And the 6.2 is about a thing called inverses. You learn pretty early in your math career, everything in math has an opposite. Adding makes you subtract, multiplying makes you divide, squaring can make you square root. The choices are endless. So yesterday we did some exponential problems. There will be an opposite of exponential problems coming soon, but before they do that, they want to give you a calculus-y explanation of inverses, a definition you've never heard of before, and then some other things. So early in the year, in Chapter 1 Algebra Review, we talked about how functions are just formulas, equations, math structures that can take a value from a thing called the domain and give it a value in the range. You didn't probably enjoy the domain and range questions back in the day all that much. We were writing those in a thing called interval notation with parentheses and brackets and stuff, if you remember that. But the basic gist was the domain was an axy thing. You plug that into this function, and out shot a y, and the y's that came out were called the range, the x's that went in were called the domain. For example, you could stick 2 in, and it would get squared, and out would shoot 4. But for cubing, if you put 2 in, out would shoot 8. This is a somewhat incomplete world for one of those. We could add a level of detail on one of these two equations because there is like another choice. Do you have an idea of what I mean? We'll come back. In Algebra 2, what we learned was a rule that to be called a function, if I stuck in 1x, I could only get out 1y. I couldn't like stick in 2 and have like multiple options. And the way we tested that was a thing called the vertical line test. It doesn't apply to today. But if we graphed x squared, what's a graph of x squared look like? A U. Everywhere I draw a vertical line, I would only get a single touch. So that qualifies that to be a function, to meet the definition of a function, which was, I stick in an x, I'm only going to get one choice out for y. I can't get multiple options out there. For example, square rooting. Square rooting did not qualify as a function, because if I gave you something like 4 and asked you to square root it, you could get either +2 or -2. So square rooting didn't make the cut. A graph of square rooting would look like this, and if I drew a vertical line, I touch it twice, and that it's not official. It doesn't make the cut as the definition of being a function. We did that in Algebra 2 some. You remember what x cubed graph looks like? Yeah, it's like the jackrabbit at Kennywood roller coaster ride. It does meet the definition of being a function because we'd only ever get a single touch out of that. If we give it a certain number, we don't get multiple choice answers. We only get one answer out of that. That's like old info. New phrase of the day, some functions are called one-to-one. The ruling on one-to-one is sort of the reverse of what I was saying a second ago. The ruling is you can't have two x's give you the same y. And now we come back to the point I was alluding to here, but we didn't quite absorb instantly, and that's okay. One of these two functions has a situation where two x's could give you the same y. And we're saying thumbs down on that if we're trying, our goal is to be classified as a one-to-one function. Can you spot which one of these would fail that test? Because it has a spot where two x's could give you the same y.
X squared.
Yeah.
-2.
If -2 goes in, 4 still comes out. We have a couple options going in that give us the same thing out. It still classifies as a function. Okay, the rule on function is that we can't have multiple choice over here. The rule on one-to-one function is we can't have multiple choice over here. So this is not one-to-one. This is one-to-one. To test that, there's a thing that somebody invented called the horizontal line test. So if we try to draw a horizontal line here, we get a double touch, and that means this is disqualified as one-to-one. up here, if we drew horizontal lines, we would only get single touches, so that's a victory being 1 to 1. And I think that's the first little tidbit of the homework, and that's not like gigantically life important, but it's a thing. Let me see if I'm right. Yeah, the first 6 questions will ask you, is this 1 to 1 or no? And they'll do that from showing you a graph. So you just imagine horizontal lines. If you touch something twice, fails the test. If you only get single touches or no touches, then it passes the test. Question about that concept? They do that whole speech to tell you that 1-to-1 functions can be reversed. And there's a thing in math called inverses, which is sort of synonymous with opposites. Square rooting was more difficult because if I said to you, I squared and now I have 4, what did I used to have? You're kind of like, I don't know. Could be 2, could be -2. That's a problem. Squaring can't be reversed the same way that cubing can. If I said, hey, I cubed, I got 8, what did I used to have? Well, definitely 2. That's a 1-to-1 function. That's one of the reasons why in Algebra 2 you were introduced to the rule that when you saw with something given to you with words, you could get those double answers. Like if I say to you with words, what are the square roots of 2? There's 2 answers. But when this symbol got used, that's only going to be allowing you to have one answer. The positive answer was called a principal value. That's like old stuff. But anyway, what they'll ask you today to do is come up with inverses of certain functions. So here's our 2 possible jobs. On a graph, which you'll probably like less, what you're going to have to do is draw the line y equals x. This is the line y equals x. And we're going to create like a mirror image. So if my original graph was like this, you'd mirror that and create the letter T. Your job would just be to do like a flip-flop fold. If I graphed you this, and you mirrored it, you create a smiley face, right? So they're not going to do fun stuff like that, but whatever the graph looks like, if you mirror it, that's what we're doing for these graphs. What you're going to do more on is work from equations. On equations, what you're going to do is switch the x and y and just do some algebra. I'd say this is more of a star idea. I'll say this is more of a superstar idea. This is more of a star idea. So you'll do some graphing where you mirror it, but you're going to do more equations. So if I said to you, here's an equation, make up an equation for the inverse. You'd start off by going x equals a half y plus 1. But then you'd want to work that until the y has been re-isolated. So how would you get that y alone? Subtract the 1 over, then multiply by 2, which you could do by distributing or by writing a set of parentheses. It doesn't matter. So this would reverse anything. For example, if I put in 4, if I put in 4, you'd get out 3. So on this one, if I put in the 3, you'd get out 4. Because x and y have mirrored each other. So this creates a result. This would undo the result you created, and it just could just run like an endless loop. So if I wanted to do this, I'd first go x equals y squared plus 2. To get the y alone. X would subtract 2.
Oh, I thought that was a Z. My
That's
bad.
all right. So x would subtract 2 first, and then we do a root. So for example, if I plugged in 1 to this original, I'd get out 3. Which means in this, if I plug in 3, I should get out 1. Do I?
Yes.
If you want to check your inverses, you can do that by just picking numbers and working with them, seeing if they invert each other. So this, I'd go x equals y plus 2 squared. It's similar to this, but we'd solve in a different order because of the existence of the parentheses. How would we solve this first for the y? Square root the x. That would get rid of the square. And then you'd have to subtract 2. And now the y would be a lunch. And I could plug in numbers, but I think you're convinced that that would work. Question about what we did on this? I'm going to step a little bit left and do a quick graph way of doing this. It's right there. If I wanted to graph this, do you remember how to graph this? I'd go up 1, and then from there, up 1, right 2. And we get a straight line. The cross point back here would have been at -2. If I had graph paper and I graphed straight, that would have just happened naturally. So if I wanted to graph the inverse, I'd have to draw the line y equals x, which means I'd be going through 1, 1, 2, 2. This is the line that would create a mirror type situation. This would be a touch point on the line, so that doesn't have to move anywhere. And then we could just change a couple of points. Instead of this being up 1, it would end up going right 1. I'll break out my colors. Use my colors very often. We're just switching x and y when we do this mirror as well. But this was up a square, so I'd make another thing that's right a square. Instead of left 2, that should go down 2. If I had graph paper, it would look better. But those have like mirrored each other. They're the same on both sides. If we wanted to graph this, how would we have graphed this just from Algebra 1 knowledge? We'd have gone down 2, which we hit that point, and then from there, up to right 1, which we hit that point. This one, this would also go up 2, and then it would be like a U-shape, sort of. So if I drew this line, instead of up 2 for the inverse, I should go right 2. And then it's sort of like that little hook, I should do more like that sort of a little hook, so that mirrored each other. If I did want to graph this, Algebra 2 experiences, x minus 2 would have headed us right 2, and square rooty graphs went that way. And I only graphed half of a u because of the whole 1-to-1. If I use this symbol, I can only stay positive, like kind of stuff. You don't have any in the homework that you have to do your own graph and then mirror it. There are some in the homework that they'll do an existing graph and you'll have to mirror it. I'm just sort of doing both of those at the same time. If I wanted to do this, this would have gone left 2, and that would be a U shape. At 0, when x is 0, 2 squared is 4. So I get a U shape, kind of like did that. If I were given that pre-existing graph and I needed to do an inverse, the left 2 would become a down 2, and the up 4 becomes a right 4. sort of create a swoopy thing, they mirror each other. So left, rights just become up, downs, X's, Y switch, and we can mirror that either by visually just happy face, or by pick a couple points and just switch them. Question about that? One second. And here's an interesting trivia tidbit, which sometimes can be a time save, and sometimes not so much. I'd say this is a very mild time save. If you have a lot of problems to do, this might come up, but rarely. The derivatives of inverses always end up being reciprocals. So I'll do a for example, and then I'll show you how you can maybe shave a corner on a rare occasion. X squared is the original formula. What's the inverse of x squared? Opposite of squaring? It's rooting. Otherwise known as x to the half. Derivative over here. Derivative of x squared? 2x. 2x. Derivative over here. Half x to the negative half. In other words, 1 on top of a 2 with a root of x. In regular world, we might be considering a point like 3, 9 could be under consideration. I just randomly picked one that would work. Like 3 squared is 9, so I just grabbed something that's not too hard to deal with. If in regular world we're dealing with the point 3, 9, this would take on the value of 6. If we're in inverse world, we're not thinking about 3, 9. We're thinking about 9, 3, because x, y trade off. So here, we plugged in the 3 for x. Over here, we want to plug in 9 for x. So plug in 9, 1, 6. This is the reciprocal of that. So if your only desire were to know this, what's your quickest path to this?
Plug in 3 to the derivative and then flip it.
Yeah. Work through this stuff and then flip it. Really, none of that is necessary because we're just going to be able to do the reciprocal of the other one. This is less fun to work with. That was a little easier formula to work with. So if you wanted to know like the derivative of the inverse of something, for something like this one, I think you'd certainly rather do the derivative of this than have to deal with the derivative of that. You don't want to do the derivative of that. You'd much rather do the derivative of this and just like get your flip on. There's a little bit of homework where they'll have you doing that. So let me make up one more in this space once I create that space. So the question may say something like, find the derivative of the inverse at x equals 6 equals f of 2, which is a bunch of math, if f of x equals x cubed minus 2. So this is what they're meaning. They're meaning that in original function world, we have the equation x cubed minus 2. This whole bit of nonsense is telling you that 2, 6 is a point in the real world. Because they're telling you they want the derivative, in inverse world, the x is 6. If in inverse world, the x is 6, in real world, it's reversed. Okay? And this, you're used to always seeing f of x, like that's how things are often written for you. This is another key to just tell you that the x is 2, like in the real world. So we won't need to step through any of that nonsense. We just need to do the derivative to get 3x squared. We need to plug in 2 to get 12. So the real answer we'd be shooting for, not at 2.6, but at 6.2 now in inverse world, the derivative would be 112. Because you probably would rather not do a bunch of stuff with cube roots and do the derivatives and plug it. So that just it cuts it order. Likelihood of a person like in their occupation needing to do that, I mean, extremely low, but it's a decent little trivia trick fact. So let's look at homework page. We already looked at touch. 1 to 6 is based on the horizontal line path concept. 7 to 12. 7 to 12, they graph U graphs, and those are meaningless. Those don't do anything other than you can see what things look like when they mirror each other. 7 to 12, there's a blue graph mirroring a red graph. What they want you to do on 7 to 12 is, from the equation, just switch the x and y and solve. And sometimes people will say to me, hey, there's no y. Well, yeah, there is. How is there a y on 7 to 12? F of x is y. So instead of f of x equals blah, 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 it's y equals blah, blah, blah. So what they're expecting you to do 7 to 12 is what I did on these 3 problems. I erased that one, but we had 3 of those. We switched x, y, and just did the algebra. That's what you're doing 7 to 12. 13 to 17, you're not using the equation, you're only using the graph. So what you want to do on 13 to 18, they graphed you a blue graph. You want to create the equivalent of their red graph from it by playing a mirror image game. You know, imagine the line y equals x and just kind of play a mirroring game. 19 to 24 is identical to what you're doing 7 to 12. So 7 to 12, you switched x and y and you solve. 19 to 24, you'll switch x and y and you'll solve. You can ignore the directions. They say a bunch more things in that to do. Just switch x and y to solve. That's all I'm asking for. 25 to 28 is 25 to 28 is just the same thing. Switch x and y, keep solving. And then they do want you to plug in. So there's a small difference addition on 25 to 28. 25 to 28, it's like what I did here. I switched x and y, and then I picked a number to plug in, and then I picked the result to plug into the other thing, and you should see that they mirror those. So like how on this I had 4, 3, and then I came up with 3, 4, and I felt like that confirmed that I was right. That's what they're doing 25 to 28, is just making sure that those, is that what they're doing? No, I take that back. You're plugging the same number into, let me read the directions again. I think I misspoke. 25 to 28, yeah, you are switching x and y and you're solving again to get an inverse formula. And then I said the wrong thing. They want you to plug into both the original and the derivative to make sure you got reciprocals. So they're doing something like this. Like, you have this formula. You make this formula. You do the derivative, you plug in. You do the derivative, you plug in, but backwards. And those are going to be reciprocals of each other. This is a sample problem of what we're trying to do, 25 to 28. And then the last little tidbit's 31, 32. 31, 32 is like the last problem I did where we're cutting the corner, where we're just going derivative, plug in, flip it. So 31, 32 like the last group, 25 to 28 like this bigger group. And I understand, do you understand? I lost myself for a second, and that's not good probabilistic. Okay. Sometimes when I lose myself, I lose track of what your facial reactions may be. Syllabus will tell you, there's some groups we're just doing the odds, it's more just doing it all, but we should cut a few quarters on a few of the sections, at least one of the sections. That's all we got.